Alright, having a little bit of trouble with my cursor here, but hopefully we can get some actual things going. So we're going to be talking about probability, and this is learning target 3. I'll hand out the learning targets on Wednesday. Alright, so let's talk about probability. We're going to start with experimental probability, but first we need to lay a few background things. So in the field of probability, we use mathematics to describe the chance or likelihood of an event happening. Okay, the most common thing that you see sometimes is like a bag of marbles, some red, some blue, and you put your hand in there and we try to think about what's the probability that you would pull out a certain color. And we'll be going back to that in a second. An impossible event is one in which there is 0% chance of an event happening. Okay? So there is no likelihood that this event will happen. A certain event, something that is guaranteed to happen, is said to have a 100% chance. Okay? So that's a 100% chance. So, for example, we go back to our marbles. We have 15 blue marbles and 15 red marbles. So think about what would be an impossible event to happen. Well, the impossible event would be to reach your hand in and pull out, I don't know, let's say, first off, it talks about the 100%. So that would be putting your hand in the bag and pulling out, let's say, just a marble or either blue or red, because the only thing in the bag is blue or red. Now, an impossible event would be more like one of pulling out a marble that is magenta. Those marbles are not, they don't exist, and they are not in our bag, so that would be an impossible event. Sorry, my pen is a little bit weird right now. Anyway. Okay, so here's a couple marbles, and let's move on. So probability between 0 and 1. We assign a number to every event which lies between 0 and 1, indicate 0% as impossible, and 1 as our certain event, which is 100%. Now, if you think about this as a scale of 100% and 0% probability, well, we can think about also the implications of something being like 0.5%. 0.50% would be the same thing as 50%. So 0.50 probability means 50%. Most often probability is shown as a decimal. Outcomes are usually shown as a fraction. So we can say the probability of something happen is 0.50 or 0.67, but we can say there are 35 out of 100 outcomes. Could be a possible way of talking about it, but I'll be probably allowing fractions in probability, but you can use decimals. When I ask for the probability of something, I will expect it in a decimal, okay, unless I say so. All right, some other key terms. So the number of trials is the total number of times the experiment is repeated. We also talk about the outcomes, and the outcomes are the different results possible for one trial of an experiment. Okay. The frequency of a particular outcome is the number of times that this outcome is observed. Right? And then the relative frequency of an outcome is the frequency of that outcome expressed as a fraction or percentage of the total number of trials. And we'll be calculating that relative frequency. And if you remember in our previous section, relative frequency was the percent of each table. And so we'll be taking a look at a table and the relative frequency and how that is represented in probability. One thing to recognize, though, is that experimental probability is the relative frequency. Alright, so let's take a look at an example here. Suppose we have this plastic cone and we toss it up in the air and we record how many times it lands on its side and how many times it lands on its base. Okay? So we toss it up in the air, and now let's think about this. How many trials were there? Well, we think about the total amount of trials, and the total amount of trials is the total amount of times it was tossed in the air. Another way of finding it is you look at the number of outcomes over here, the sides, and the number of outcomes on the base. Add those two together and you get your total number of outcomes. Gosh, why is this doing that? So there are 270 trials, a total of 2 outcomes. So you can also see it as 157 plus 113, we get 270. Okay, what are the 2 possible outcomes? You can answer this on your own if you want. You can always pause the video and answer these. The 2 possible outcomes, that would be landing on its side, landing on its base. What are the frequencies of the 2 outcomes, respectively? Well, sides, we have 157, and base, we have 113. So 113 times it landed on the base, 157 times it landed on its side. So, just to draw it out for you, we have our cone here, and we toss it up in the air, and we're looking to see whether it, oh golly, what's going on? Lands on its side, like this up here, or lands on its base, which is flat, like up here. So what is the relative frequency of both outcomes respectively? So let's go ahead and go to the next slide and take a look at that. Okay? Relative frequency, we take the number of, let's do side. Actually, sorry, I'm supposed to calculate this. So let's go ahead and do that. So it's the number of outcomes for 1, so that would be like 157, and we divide it by the total outcome, which for this one would be 270. So we take our handy dandy calculator, do that, and we end up getting 0.5815, and that would be our relative frequency. Now, that being said, if we were to convert that into percentage, we would say that that is a 58.15%. Now, 58.15% what? Percent chance of it landing on its side. Okay? Okay. So let's talk about the notation. The last question we saw, the probability that the cone will land on its base is something. Okay? So we can use this particular notation. This notation is the probability, right here, it says P, P is probability of the event, which this particular event is base, and we look at that and we say that equals our number of specific event outcomes over the total number of outcomes or the number of trials. Okay? So the frequency of a particular outcome over the entire frequency of the entire experiment. So we end up getting 0.4185 respectively. The capital B is used for probability, and within the parentheses is a possible outcome. So you could try that for sides, which I accidentally did already. There's your answer. I already did it on the other page. Awesome. Now, I did want to point out what the heck does respectively mean. Respectively is used because the outcomes are based on prior trials. Okay? So there was 270 trials, and we're trying to make a prediction over all outcomes based on a cone being flipped. Okay? So a cone's flipped 113 times it lands on its base. So we can say the probability is about 41.85%. Okay, we can convert these probabilities to percentages. So 41.85%. Okay. So respectively means according to our particular cone, according to our particular data set, all that kind of stuff. So let's take a look at a coin toss here. We're taking the Brazilian coin. And suppose we have one coin. What are the possible outcomes? Well, if we think about it, we toss a coin up in the air. There should be two possible outcomes. One of those is heads, and one of those is tails. Okay, so we have tails here, and we have heads. So if we take that, and it says, if we toss the coin, what would the probability be for one of those possible outcomes to occur? Well, let's take heads or tails, and let's go ahead and do that. So heads occurs once. Our total number of trials is two possibilities. So we have one of the two happening. We would end up getting a 0.50% chance. Oops, not change, but chance. Okay, so let's take a look at two coins. Suppose we have two coins. Well, what are the possible outcomes for those? Well, we toss a coin. The first coin we toss, and it's tails. The next coin we toss is tails as well. So that's one possible outcome. Okay, do it again. We get heads and heads. That's another different possible outcome. The other difference would be tails and heads. That is a third possible outcome. And then the first one could be heads, and the second one could be tails. So we have four possible outcomes. So think about this. If we toss the coin, what would the probability be for one of the possible outcomes to occur? Well, we have four different outcomes, total outcomes, and one of them occurring. So we have a 1 in 4 chance of any of these occurring. That would be a 25% chance, or 0.25 probability. Okay. Now it's interesting. I said note that the order matters. Well, these two right here, tails and heads, it's very similar to heads and tails, but we're looking at individual coins, and we're looking at order, and order does matter. Okay, now we're going to be talking about when order doesn't matter and what are the possible outcomes in regards to that. Okay, so in class, make sure you bring some change. We're going to be doing a few coin tosses and whatnot. Maybe I'll get some dice out as well. Alright, so we need to estimate probabilities from data. Alright, so stats can be used to calculate probabilities in many situations. So check out this situation that I drummed up from the book. It says the table shows the number of short-term visitors coming to Australia in the period April to June in 2011, and the main reason for their visit. Alright. It says find the probability that a person who visited in June was on holiday. Find the probability that a person coming to Australia arrived in May. Lars arrived in Australia in April, May, or June in 2011. He came to visit his brother. What is the probability that he arrived in April? So let's take a look at these individually. So the first one, A. This says, find the probability that a person who visited in June was on holiday. So we look at the total number of people who visited in June. This is the total. And we want to think about how that is related to holiday. Well, this many people during the month of June were on holiday in June. And so we can say that we take our, and the notation is the probability that on holiday in June. We take on holiday in June. So on holiday in June is 156,500 over the total amount, which was 308,300. So this is the number on holiday in June. Jeez, it's really messing up right now. Versus total people in June. Okay, and we do that, and we end up getting about, oh golly, Josephith, I get about 0.508. So, what about B? B says, find the probability that a person coming to Australia arrived in May. Okay, well, we have to think about this as a total of May. So this is the total in May. And we also have to think, well, this is also the entire visitors in Australia. So we're not even considering any of the main reasons for the journey. We're just considering how many people visited Australia. Okay, so we say the probability that they arrived in May and we put the number of people who arrived in May, which is 260,900. Put it over the total amount of people. So we take this and we add all of these up to get the total amount. And that turns out to be 890,700. And we end up getting a nice value of, let's see, 0.293 or 29.3%. We're in May. Alright, so let's take this last one. Last one's a little bit more confusing. It says Lars arrived in Australia in April, May, or June. He doesn't know his own time he arrived. He came to visit his brother. What is the probability that he arrives in April? Okay, so we say this dude came to Australia to visit friends or relatives during this period. Okay, so we have friends or relatives. Where's my cursor? There it is, and it's writing all over the place. So we have friends or relatives. We would want to add all of these up to get the total amount of visiting friends and relatives. So we add them all up. We end up getting a nice value of 100 and, let me see, let's drag this here, 190,100 total. Now he wants to know the probability that it would be in April. So in April there was 77,500 possible cases. We divide that by the total amount of visiting friends and relatives. That would be 190,100. And we end up finding out that there is roughly a 0.408 chance. So that is 40.8% chance. So this is our probability. And we can put little dots or whatever because my stupid cursor's not working properly. Alright, so let's move on to the universal set. Ooh, it looks like I have given the answer. So, let's go ahead and read through this. The universal set, denoted as U, is the set of all possible outcomes. This is sometimes referred to as the sample space, not the sample set. For continuity, we will refer to U as sample space or universal set, depending. So how to represent a sample space, you ask? Here are a few ways. The first way is listing the possible outcomes. So
we use set notation to show these possible outcomes. So we're going to take rolling a die, and we're going to be using that throughout each one of these examples. So there are 6 possible outcomes. You can roll a dice and you can get 1 through 6. So we say sample space then equals, and that's 1, 2, 3, 4, 5, or 6. Okay? Now this little symbol right here, that means therefore. This is the mathematical term for therefore. 3 little dots. Ooh, okay, good. So, here we go. Ooh, that looks pretty, doesn't it? When rolling a pair of dice, so 2 dice, we can use a 2-dimensional grid, okay? And these 2-dimensional grids explain each particular outcome, okay? So we can look at this grid and we can say, okay, here's 1 die over here, 1 die, and here's the other die, okay? Now, what are the probabilities? Well, if you look, we can count all of these up. The total amount would be 6 times 6, which is 36 possible outcomes. So there's 36 total dots, and suppose I want to figure out when the first die rolls a 5 and the second die rolls a 6. Well, we can look at this. This is second die. We can look at this and say, okay, 5 and 6. So first die rolls a 5, second die rolls a 6. This would be one of those 36 possibilities. Now suppose we want to figure out if it wasn't exclusive. Okay, so let's say we say the possibility that one of the dice is 5 and one of the dice is 6. So we can look and say, okay, 5 and 6. So here's another possibility right here. So we have 2 possibilities. Okay, so this is if this is order matters. So we have a 1 in 36 chance. And this one is if order doesn't matter, 2 in 36. Can we reduce that? Absolutely to 1/18. So order, piece of crap. We'll be talking about that later. It's called exclusive events and non-exclusive events. Oop, let me go ahead and move my little cursor crap here. So this is away. There we go. Alright, so it says each of the following cross sections represents an outcome. When you roll a die, you can have one of these particular outcomes. And yes, I labeled all 36 of them. So 1 and 1 can occur. 2 and 1 can occur, and 1 and 2. This represents this particular spot here. Our first die and our second die represents this spot, and so on and so forth. Okay, this first row represents this whole first row here, second row, third row, and so on and so forth. Okay, 11, 1, 1 represents a 1 being rolled and a 1 being rolled. So this is useful. This is really useful for dealing with 2 events occurring, like 1 dice and another die, or a pair, or a lot of times 2 different things, like 2 coins, or I don't know, 2 random number generators and whatnot, and that can give you a good outcome. Unfortunately, it doesn't work with 3. So what is another way? That is the tree diagram. So we're going to be taking a look at 3 different coins, and we're going to use 3 different coins, and we're going to be doing a tree diagram. And notice I said a 2D grid would not be helpful. How would we do that? Well, we'd have to have a 3D grid, and that would be more difficult. Okay? So each branch, so each one of these represents a given outcome. So first off, we have our first toss. Okay? We don't really put anything here. This is not even a box. You usually just start with a line that goes out. I'm using a particular program that makes this kind of stuff. So here's our first coin toss. And our first coin says we get a head or a tail. So suppose we got heads. Okay? So this is what happened. Now we also have a second coin. So the second coin says, okay, here's another possible outcome. It can be heads or tails. So suppose it was heads again. Okay, so this one has another possible outcome with our third coin, heads or tails, and suppose we have heads again. Okay, so the tree diagram gives us every single possible outcome with multiple outcomes, and we can keep doing this for fourth coin, a fifth coin. Now what we can do is count the amount of possibilities and discover how many there are. Okay, so we can count this out if you'd like. We'll be actually looking into it a little bit later in the year, not necessarily right now. But keep that in mind, okay? I believe this is 2, okay? And this is 4. 2 here and 2 here, so there are 4 different outcomes. And this last one, there are 2, 4, 6, and 8 outcomes here. And so we can say when we toss something, there's 2 times 2 times 2. That ends up being 8, or 2 cubed equaling 8. So we have our first coin, our second coin, and our third coin. These are all of our possible outcomes. Okay? So if we're looking at the heads possible outcome, that would be a 1 in 8 chance. Because it's just one of those pathways being drawn. If I said first it's heads, then it's tails, and then it's heads again, well, that's also a 1 in 8 chance. If it's tails, and then tails, and then tails, it's a 1 in 8 chance. Alright, that's the end of my lesson, and hope you enjoyed it. Here's your homework for tonight. This is due Wednesday. Alright, have a good one. Stay safe. Hopefully my pen works better next time.